Hi students, in this final video for online lecture 3, we are now going to talk about the unit of chemist, the mole. So what is the mole? The mole is a unit to count the number of particles. So as you can think of various different occupations out there, they have units that are specific to their occupation. So let's think about dozen. We typically use that for bakers, that means 12. Or if I talk about a pair, that means 2. But what about chemists when we have so many particles that are so small that we can't even see them? Well, we needed to create a unit for us so that way we could count all of our particles much easier. So we came up with the mole. It is the amount of a substance that contains as many elementary entities that could be particles, it could be atoms, it could be anything. Entities means just a typical quantity, as there are atoms in exactly 12.00 grams of carbon-12. So 1 mole equals Na. Na is what we call Avogadro's number. This is the individual who studied this amount and determined this amount. This value is 6.0221415 times 10 to the 23rd. But all those decimal places is just showing off. So what I want you to remember is 6.022 times 10 to the 23rd. So this means that we can have moles of atoms, we could have moles of ions, we can have a mole of whatever we want, and it will come out to that number. So what do we want to have a mole of? Well, let's go and try something crazy. I want to have a mole of peanut M&Ms. This would be the greatest day of my life. So let's figure out just how big this really is. 4.25 million peanut M&Ms will fit in a commercial sized dump truck. I've done the calculations. It's pretty close. How many dump trucks would I need to have 1 mole of peanut M&Ms put in all of those dump trucks? So let's figure out exactly how I would do this. So what I would need to do in this case is start with a mole. So that is 6.022 times 10 to the 23rd M&Ms. Well, now what we know is that we can create a conversion factor. I am going to divide this by 4.25, so that's 4,250,000 M&Ms per dump truck. So now my M&Ms will cancel, and now I have the dump trucks on the bottom of my denominator, which means it would go to the top. So this would then give me a successful conversion factor to tell me how many dump trucks I would need. That answer is 1.42 times 10 to the 17 dump trucks. Now, you're probably wanting to ask yourself exactly how many dump trucks that is. Well, it seems like when you're on the highway trying to get somewhere, there's always one in front of you. So it might seem like there's actually a mole of dump trucks, but there really isn't. There are pretty close to about 400 million dump trucks in the entire world. 400 million. That would end up actually being 4 times 10 to the 7th. This is 10 orders of magnitude beyond that. So we would have to have more dump trucks getting created in the history of mankind in order to carry all of these M&Ms. That is just exactly how big a mole really is. So let's actually see what it means to us in a chemical sort of manner. Instead of having a mole of dump trucks, you can now see I have a mole of certain elements. In the upper left-hand corner, I have a mole of carbon. Upper right-hand corner, I have a mole of sulfur. I have a mole of copper, a mole of iron, and then if you notice there in the middle, I have a mole of mercury. but you have to notice they all don't look the same. That is because a mole has the same number of particles as the other compound, but it doesn't mean that they have the same mass. So if your sample looks smaller, it might mean that your particles just have less mass individually. Each one of these species have exactly 6.022 times 10 to the 23rd atoms of these specific elements. So what can we do with that information? Well, let's go ahead and look at the periodic table for this. If you think about this, the molar mass, the mass of one mole, can be found located beneath all of our elements. So if I want to look at iron, you can see here that I have a mass of 55.847. That's important. So if I want 1 mole of iron, that is the mass that I need to have. So let's say that I want to go to tin. If I do tin, that is 118.71. So these masses become incredibly important for us as we start to build more and more complicated species, especially when we start adding our atoms together to form compounds. So let's try this example to finish up chapter 2. The atmosphere of Earth has a total mass of 5.15 times 10 to the 18th kilograms. The concentration of methane is 1.7 grams of methane for 1 megagram of atmosphere. How many moles of methane are there in the atmosphere? Okay, this is going to be a lot of unit conversion, but we can do this. So let us go and do a conversion from kilograms to megagrams. So if we do that, I will have 5.15 times 10 to the 18th kilograms of atmosphere. So what I will do is go to our standard unit, which is going to be our gram. So 1 kilogram is 1,000 grams, or 10 to the third. What I can do now is then multiply this back in order for us to get the megagram. If I do that, I will want to have 1 megagram is 10 to the 6th grams. So if I go and do this multiplication, it's actually going and dividing by 10 to the third. So that should give me 5.15 times 10 to the 15th megagrams. So now that I have my units in megagrams, I can go and calculate by a simple unit conversion just exactly how much methane is in here. So if I go and say 5.15 times 10 to the 15th megagrams, I will multiply that and say that I get 1.7 grams for every 1 megagram. But it's really important that we label which one we're getting. So the 1.7 grams is going to be our methane, while our megagrams is going to be our atmosphere. So if I do this calculation, I should end up getting a correct number of our grams of methane. But I don't want grams of methane. I need moles. So now what I need to go and do is multiply this by the molar mass of our methane. So 1 mole of our CH4 is going to be the mass of the entire part. So if I've got carbon and 4 hydrogens, that is going to be 16 grams of my CH4. So my megagrams and megagrams are canceled. My grams of methane, I'm left with moles of methane. And if I've done this calculation correctly, I will get 5.47 times 10 to the 14th moles of my CH4. So you can see just how important the mole is, and this is just a brief introduction of the calculations that we are going to use with Avogadro's number and the mole. And once we get into stoichiometry, we are going to be using this even more and more, and you should be ready to use it anytime we need it. Have a great day.